So I'm going to finish off chapter 6 and start chapter 7 today. The upcoming test will only include the stuff from chapter 6. So homework number 4 on chapter 5 is due today. Homework number 5 on chapter 6 is due in a week on the 6th. Next week on Monday, we will do a review of chapters 1 through 6. That'll be on Monday. Then on Wednesday, we will have our test on chapters 1 through 6. Around 10 questions, each worth 10 points. And today we'll have a lab, the shorter lab. It's on stability. Any questions about any of this? I haven't fully reformed the test, but it's around 10 questions. So the last part we had left, we had a little bit of circular motion left. The circular motion, if an object is moving in a circle, it has to have a force acting on it, otherwise it would move in a straight line. And the direction of the force is towards the center of the circle. Now where did that anything go? I had a mass on a string, but everything is in chaos. Apparently. Oh, it's here. I had hidden it away from my site. So here, for example, as this moves in a circle, it has to have a force moving it towards the center. The force is coming from the string. It's pulling in towards the center. So that force, the centripetal force, is mass times velocity squared over the radius. I can quickly derive that from with calculus if you want me to. So if you start with at the position, if x is radius times the cosine of, it will be, there's 2 pi every period. The period is going to be 2 pi of the radius. It comes out to velocity over radius times time, because this has to be 2 pi over period, which is 2 pi over 2 pi radius over velocity. The 2 pi's cancel and you get velocity over radius. And y equals r sine v over r times t, and vx, vy equal r, this is minus r sine v over r t, except this is times v over r, so minus v, and this is derivative of sine is cosine, so this is v cosine v over r t, and then acceleration x and acceleration y are v squared over r, so minus v squared over r cosine v over r t, and then minus v squared over r sine v over r t. You just take the derivatives 3 times. But yeah, the magnitude of the force is mass times velocity squared over radius. The force can be provided by tension in a spring, the normal force, friction, or other. And of course, the centripetal acceleration is v squared over r. These are some examples. And if an object is changing its speed as it moves in a circle, then in that case, there's also a tangential acceleration. And you would combine them. There's not going to be any questions with tangential accelerations on the exam. Just so you know, here we have a centrifuge that spins at a rate where the bottom of the test tube has a linear speed of 90 meters per second and is 9.25 centimeters from the axis of rotation. What is the centripetal acceleration here? So we know the velocity, it's 90.6 meters per second. We know the radius, it's 9.25 centimeters. We want to find the centripetal acceleration. So centripetal acceleration is just speed squared over radius. So our radius is 9.25 centimeters. Our velocity is 90.6 meters per second. We want to find our centripetal acceleration. So the centripetal acceleration is speed squared over radius. So that's 90.6 meters per second over 0.0925 meters. And that's 88,700 meters per second squared, which is 9,055 G. If you want to compare it to other centrifuges, they're usually measured in Gs. So for example, the centrifuges in the room across the hall for large tubes cap out at 15,000 G. And then they can do more for smaller tubes, about double that. But you know, the centrifuges we have go up to 15,000 for large tubes like this. So that's on the scale of professional centrifuge. So, summary of chapter 6. Friction is due to microscopic roughness. Kinetic friction is mu kinetic times the normal force. Static friction is mu static times the normal force. And that is the maximum for static friction, because static friction is whatever it needs to be to stop the object from sliding. Tension is the force transmitted through a string. The force exerted by an ideal spring, Fx, is minus Kx. An object is in translational equilibrium if the net force acting on it is 0. Connected objects have the same acceleration. So that's a useful fact. The force required to move an object of mass m in a circle of radius r is mv squared over r. So let's start chapter 7 about work and kinetic energy. So here is a car moving up a hill with various forces and how you can figure out the work done by each of those forces. So we'll start by talking about work done by a constant force. Then we'll move on to kinetic energy and the work energy theorem. Then work done by a variable force, and then power. So if the force is in the same direction as the displacement, work is just force times distance. The unit for work, the SI unit, this is force times distance. This is newtons times meters. This is not watts. Oh. The work, units is newtons times meters. This is joules. The joule is equal to a newton meter, or kilogram meter squared. Per second squared. And that is a joule. So some typical values of work. The annual US energy use works out to about 8 times 10 to the 19 joules. The eruption of Mount St. Helens was around 10 to the 18 joules. Burning a gallon of gas produces about 10 to the 8 joules of work. The human food intake per day is about 10 to the 7. We're not very efficient. Melting an ice cube takes about 10 to the 4 joules. Lighting a 100-watt light bulb for 1 minute takes exactly 6,000 joules. Lifting a 100-watt light bulb takes less than that. A heartbeat is about half a joule. Turning a page of a book is about 10 to the minus 3 joules. The hop of a flea is about 10 to the minus 7. And breaking a bond in DNA is about 10 to the minus 20. So, if a finch can exert a force of 217 newtons with its beak as it cracks open a seed, if the beak moves through a distance of 0.42 centimeters as it does this, how much work is done? So remember, work is force times distance. So the force is 217 newtons. The distance is 0.42 centimeters. We're looking for work. In general, work is force times distance if the displacement and the force are in the same direction. So, like, if I'm applying a force and the object is moving in the same direction as I'm applying the force. We'll get into the more general case, but so 217 newtons times 0.0042 meters gives us 0.912 joules. Reasonably large force, very small distance, small work. Here we have an intern that pushes an 87 kilogram patient on an 18 kilogram gurney with an acceleration of 0.55 meters per second squared. So we're going to use, from previous chapters, force equals mass times acceleration. How much work does the intern do in pushing the patient and gurney through a distance of 1.9 meters? Assume the gurney moves without friction. And how far must the intern push the gurney to do 140 joules of work? So this is also fairly similar. First, we need to figure out, so what do we know? The mass of the patient, it is 87 kilograms. The mass of the gurney is 18 kilograms. Our acceleration is 0.55 meters per second squared. So we need to figure out the force. We also know that the distance is 1.9 meters. We want to find the work. To find the work, we need to know the force. And then we want to find the work. What distance would give us a work of 140 joules for part B? So, work is force times distance. Force is mass times acceleration. So the force is going to be the mass of the patient plus the mass of the gurney times the acceleration. So 87 kilograms plus 18 kilograms, that's 105 kilograms times 0.55 meters per second squared. That comes out to 57.75 newtons. I'm not rounding it yet, so I'm not done. 57.75 newtons times 1.9 meters gives us 110 joules of work. Which I have rounded off. Now, to figure out how far you'd have to push this to hit 140 joules of work. What's going on? Again, work equals force times distance. Distance equals work over force. So 140 joules divided by 57.75 newtons gives a distance of 2.42 meters. Or I guess probably it should be rounded to 2.4 meters. Because it's 2 sig figs on everything. Now, that is the formula if force and distance are pointing in the same direction. This is not always the case. Sometimes distance and force are at an angle to each other. So, the displacement and the force can be in different directions. So the more general equation is actually, as a vector equation, it's work equals the dot product of the force dot the displacement. So I guess you'd call it like delta x or something. I'll just call it u. But if you want to figure out what those numbers are going to be, dot products work out that work will be the force in the direction of motion, the force times the cosine of theta times the distance. So it's force times distance times the cosine of the angle. And there's like two ways you could interpret this. You can think of this as the force in the direction of motion times the distance covered, or you can think of it as the displacement in the direction of the force times the force. So those are the two ways you can think of it. You put the cosine on the force, that's the component of the force in the direction of motion. If you put the displacement on, if you put the cosine on the displacement, that's the component of the displacement in the direction of the force. And thinking about it in those ways, switching back and forth, is sometimes useful. Because sometimes the direction of the force is real obvious. Like if you're going up and down, or if the force is gravity, then what you're interested in is just the change in height. And sometimes you're more interested in the distance along the direction of the force. So that's the distance along the direction of the force. But other times, if you have some force being applied to something moving like horizontally, and it might be down at an angle, you're interested in just the component of the force in the direction of motion. But both of those work out to force times distance times the cosine of the angle between them. Which, because strictly speaking, it's a dot product of the vectors. The dot product of the vectors has magnitude. Well, actually, this doesn't have a vector on it. Sorry, it's not a vector. Dot products aren't vectors. It has size, force, magnitude of vector 1 times magnitude of vector 2 times the cosine of the angle between them. So it's maximum when they're pointing in the same direction. It's minimum, it's 0 when they're at right angles. And it's negative when they're pointed in opposite directions. So you can write it as the dot product of the force and the displacement. I forgot that was the case. So here you have the force is mg down, and the displacement is along the diagonal. And then, like in this situation, because of what's given, it's easier to think of d cosine theta. The component of the displacement in the direction of the force, because that's actually given in the problem, the height. So the work that's done can be positive if the force and the displacement are pointing in the same direction, rough or more or less in the same direction. The angle between them is between negative 90 degrees and positive 90 degrees. It can be 0 if the angle is 90 degrees, and it can be negative if the angle is between 90 degrees and 270 degrees. It's more than 90 degrees. They replaced the windows, so there's something. And if there's more than one force acting on an object, you can find the work done by each individual force and add them up. Or you can find the net force and find the work done by that. And those will always come out to be the same. So the total work is the total force times the cosine of the angle times theta. You can either add up all the forces, find the net force, or you can do the individual works from each force. Both are options. Sometimes it's easier to find the net force. There's something that will make it pretty clear. Sometimes it's easier to add up the works from the individual forces. So yes, the calculus definition of work is it's the integral of force dot dx from your initial position to your final position. And thus, if force is constant, work ends up being force dot displacement. The displacement is a straight line. No, force is a constant, work ends up being force dot displacement. So here we have a gravity escape system where an enclosed lifeboat on a large ship is deployed by letting it slide down a ramp and then continue to free fall into the water below. Suppose a 4,970 kilogram lifeboat. Remember, the weight of a lifeboat is going to be mg. Well, that's not, maybe I shouldn't use W for weight because W is work. That's one of the problems we can have. But remember that the force of gravity is mg. So suppose 4,970 kilogram lifeboat slides a distance of 5 meters on a ramp, dropping to a vertical height of 2.5 meters. How much work does gravity do on the boat? So just a reminder, G is equal to 9.81 squared in this boat. So what do we know? Mass is 4,970 kilograms. Height is 2.5 meters. The distance along the ramp is 5 meters. G is 9.81 meters per second squared. We want to find the work. To do that, we need to know the angle and the force. Well, the force is mg, so work is force times d cosine theta. To find theta, well, the force is mg, so we can just plug in mg. D is 5 meters. But it turns out, if we look at this triangle, h, the height, is d cosine theta. Because, oh, sorry. Now this length is d, and this is a right angle. So d over h is cosine theta. So height is d cosine theta. Given that height is d cosine theta, height over d is cosine theta. We can plug in height over d for cosine theta. We get work as mgd times height over d. Work ends up being mgh. The work done by gravity is mass times g times the height that you travel downwards. So 4,970 kilograms times 9.81 meters per second squared, that's 2.5 meters, which is 122,000 joules. So here we can look at two different ways to raise a box up to a height, to a final position. We want to load a box into the back of a truck as shown in the sketch. One way is to lift it directly upwards so that we are applying a force countering mg to lift it up to a height h. The other is to slide it up this ramp, doing work, so that does work W1. The other option is to slide it up the ramp, doing work 2. Assuming the block slides on the ramp without friction, so this force to slide it up the ramp, we would have two forces. We would have, the force we would apply is counteracting the component of gravity down the slope. So it would be mg sine theta, sine phi, where phi is the angle of the ramp. Or we just have mg and the height. But we'd be traveling the whole length of the ramp. So which of the following statements is correct? Is work 1 less than work 2? Is work 1 equal to work 2? Or is work 1 greater than work 2? Which of these do you think requires you doing more total work? Lifting it straight up and putting it to this height, or sliding it up the ramp? Now, which is harder, which requires more work? So, who thinks work 1 here is less than work 2? Who thinks this method does less work than this one? Who thinks they do exactly the same amount of work? I got some yeses there. Who thinks this one does less work than this one? Well, the few yeses were correct. They are equal. Work equals force times distance times cosine theta. In the first case, work 1 is force 1 times height, which is force 1 is going to be mg, height is h. Work 2 is force 2 times length times cosine theta. Force 2 is mg sine phi times length. Cosine theta is, in both of these cases, is just 1. Height over length is sine phi, so we can substitute. So height is equal to length sine phi. So we can substitute in length sine phi length for height, and we get work 2 is equal to mgh. So work 1 equals work 2. Now, this method is, of course, easier because you don't have to provide as big of a force, but it does the same amount of work because you provide a smaller force over a longer distance. And because you're working against gravity, which is a conservative force, it ends up working out to the same amount of work. We'll get to that later. So here we have a car of mass m that coasts down a hill, inclined at an angle phi below the horizontal. The car is acted on by 3 forces. There's the normal force perpendicular to the road, exerted by the road. That's force I. Force II. Force 2 is the force due to air resistance, pointing backwards against the car. And then lastly, there's the force of gravity, mg, pulling the car down. We want to find the total work done on the car as it travels a distance d along the road. So the angle for force 1, the normal force, the angle between the normal force and the displacement is 90 degrees. For force 2, the air resistance, the angle between the air resistance and the displacement is 180 degrees. And for force 3, the force of gravity, the angle between the displacement and gravity is 90 minus phi. So here we have this car rolling down the hill. Let's go through and work out the work done by each force. Work is force times distance times the cosine of the angle between them. Let's start with work sub I. That's going to be the normal force times the distance times the cosine of 90 degrees. That will be the normal force times the distance times 0, because the cosine of 90 degrees is 0. If a force is at right angles to the movement, it does no work. So that's 0. Work 2, the force of the air times the distance times the cosine of 180 degrees. Cosine of 180 degrees is minus 1. So this is minus force air times distance. Work 3, force of gravity times the distance times the cosine of 90 minus 5. So 90 minus cosine of 90 minus phi is the sine of phi. That's our first substitution, the trigger identity. And force of gravity is mg. So mgd times sine phi. And our total work is going to be work 1 plus work 2 plus work 3. So 0 minus force air times d plus mgd sine phi. Or if you pull out distance times mg sine phi minus the force from the air, the drag from the air. The force down the slope from gravity minus the force back from the air. So this is just the net force down the slope. Any questions? So, kinetic energy and the work energy theorem. So, when positive work is done on an object, its speed will increase. When negative work is done, its speed will decrease. So this is something you can observe. When you do positive work on an object, it speeds up. For example, I will allow gravity to do positive work on my clicker. It sped up. And then the book did negative work on it, and it slowed down. So as an apple is falling, the work is positive, the speed increases. If you toss an apple upwards, the work is negative because the displacement is opposite the force. So the speed decreases. Turns out we can relate this. If we do a few algebraic manipulations of the equations of motion, specifically the v squared equals v naught squared plus 2a delta x, we can find that the total work equals 1/2 mass times final velocity squared minus 1/2 mass times initial velocity squared. Would you like me to derive that, or are you okay with just that equation? Because I can quickly derive it if you want. I'll quickly derive it. Takes a moment. So we have velocity squared equals initial velocity squared plus 2 times acceleration times delta x. So 2 times acceleration times delta x equals velocity squared minus initial velocity squared. Divide everything by 2, we have acceleration times delta x equals 1/2 velocity squared minus 1/2 initial velocity squared. I guess these would be final and initial, final and initial, final and initial. And we'll multiply everything by mass. The mass times acceleration times delta x equals 1/2 mass times velocity final squared minus 1/2 mass times velocity initial squared. Mass times acceleration is force, delta x is distance. So this is just work, is 1/2 mass velocity final squared minus 1/2 mass velocity initial squared. So this is called the work energy theorem. And this quantity that is related to work called 1/2, that is 1/2 mass times speed squared. We define that to be kinetic energy. So this can be rewritten, let me get a better marker, as just total work is kinetic energy final minus kinetic energy initial, or change in kinetic energy. Your book uses a capital K for kinetic energy. Sometimes people will use E sub K. Yeah, but that is the work energy theorem. Work is equal to the change in kinetic energy. So the total work is equal to the change in kinetic energy, and kinetic energy I'll go over here and get rid of the unit bit. I'll just write out the more general work. Work is force times distance from cosine of the angle. Total work is equal to delta K. K is which is 1/2 the final square minus 1/2 the initial square. K is equal to 1/2 mv squared. This is the work energy theorem. It relates work to kinetic energy. So energy, kinetic energy has the same units of work. It's in joules. So work is energy. It's just a specific case of it. So a small plane moving along a runway has a mass of 690 kilograms and a kinetic energy of 25,000 joules. What is the speed of the plane? And by what multiplicative factor does the kinetic energy increase if the speed is tripled? And remember, kinetic energy is 1/2 mass times velocity squared. Mass is 690 kilograms. And then I erase this derivation. Kinetic energy is 25,000 joules. And we want to find the velocity. Kinetic energy is 1/2 mass times velocity squared. So 2 times kinetic energy over mass equals velocity squared. The velocity is the square root of 2 times the kinetic energy over the mass. So if we plug in our values, 2 times 25,000 over 690, take the square root. Did I seriously screw up the animation? No, I just forgot to put the actual number in. Apparently. This is 8.5 meters per second. The animation. Sorry about that. Apparently, I just forgot to put the actual value in. The 2 times 25,000 joules over 690 kilograms comes out to 8.5 meters per second. I don't know why I made that mistake. I'll re-upload these slides. Now, if our initial kinetic energy is 1/2 mv squared, if we triple the velocity, we have 1/2 mv times 3 times the velocity squared. That's 3 squared is 9. So 9 times 1/2 mv squared. So that's 9 times kinetic energy y. So if we triple the velocity, the kinetic energy increases by a factor of 9, or 3 squared. if you have a 220 kilogram motorcycle cruising at 14 meters per second, what total work needs to be done on the bike to increase its speed to 19 meters per second? So this, we know the mass, we know the initial speed, we know the final speed. So we can use the work energy theorem to find the work required. So, we know the mass, 220 kilograms. We know the initial velocity is 14 meters per second. We know the final velocity is 19 meters per second. And we want to find the work. Well, work is just change in kinetic energy, so it's 1/2 mass velocity final squared minus 1/2 mass velocity initial squared. That works out to 1/2 mass times the different v final squared minus v initial squared. So 1/220 kilograms times 19 meters per second squared minus 14 meters per second squared. 19 squared minus 14 squared is 165. So 1/2 times 220 kilograms times 165 comes out to 36,300 joules. Or rounded to two significant figures, 36,000 joules. You know, because we have the test coming up, I'm going to stop there for today. We'll continue this after the test, and we'll start the lab early so you can get out of here earlier and get ready for the test. Let me stop.